reduce the energy waste. Due to the large energy waste in the transistors, we need to charge our cell phone every day. So it is significant to find low power transistors. For the power consumption problem in the semiconductor industry, the topological states may be a solution direction. On the edge of two-dimensional topological insulator, the spin-up electrons and spin-down electrons move in the opposite direction. The hybridization between them is forbidden by the transversal symmetry. If there is a defect in the sample, the electron will detour around the defect. So there is no backscattering of those electrons, which greatly reduces the energy waste. When the transversal symmetry is broken, we can find the characteristic state in the quantum normal Hall insulator. So even the hyperloop can be realized in the topological states. Given those promising properties of topological states, we may only need to charge our cell phone weekly or even monthly. In addition to the power consumption problem in the semiconductor industry, the computer performance is also improved very slow, especially since 2004. Then quantum computing is proposed to overcome this difficulty. In the classical computer, the bit can only be 0 or 1. In the quantum computer, the qubit is a superposition state of two degenerate states. The qubit has far more computing power than the classical bit. For example, there is a paper from Google company. For a specific task, the quantum computer takes only 200 seconds, where the classical quantum supercomputer will take nearly 10,000 years. However, the decoherence of the quantum state is a major hurdle towards reliable and scalable quantum computing. In order to keep each qubit working properly, several error correction bits are needed. Then topological quantum computing is proposed to realize the fault-tolerant quantum computing. There are many ways to use the topological states to realize the topological quantum computing. Here I introduced a way based on topological insulator. For the derived surface states of three-dimensional topological insulator, the spin and the momentum are located. Once S-wave pairing is introduced, we can realize the topological superconductor. When magnetic field is applied in these systems, we can find the marginal fermion as the vortex center. The marginal fermion is equal to its own antiparticles and obeys the non-abelian statistical. As the marginal fermion are protected by global topological invariance, they are robust against the local perturbation. So we can use the marginal fermion to realize the fault-tolerant quantum computing. In topological states, there are fruitful magnetical, electronical, and optical phenomena, such as the current anomaly. In 2016, the Nobel Prize in Physics was awarded to Solis, Houdan, and Kosteris for theoretical discovery of topological states of matter and the topological phase transitions. So what are topological states? Here I take topological insulator and the direct semimetal as examples for illustration. For topological insulator, the bulk is insulating, which is similar to the normal insulator. However, we can find the gap response states in the bulk gap. For the derived semimetal, there are discrete band touching points around the Fermi level. The degeneracies of the band touching points are fourfold, and we usually can find the Fermi arc surface states on the boundary. Band inversion is a hallmark of topological insulator. For normal insulator, if we move the conduction band towards the valence band, at the critical point, they touch each other, and the distance is a direct semimetal. After the critical point, the conduction band and the valence band are inverted, and the distance is a topological insulator. In order to describe topological states, topological invariants are introduced, such as the term number is defined for the derived semimetal. Although there are many different topological invariants, The definitions are based on the Berry phase. In quantum mechanicals, we learned that the wave function acquires a Berry phase once the system is subjected to a cyclical adiabatic process in the pyramidal space. It was noting that the Berry phase is gauge invariant and related to some physical observables. For storage, the pyramidal space is the momentum space. As the k points are periodical in the momentum, so we can put two equivalent k points together and get the one-dimensional closed loop. Next, I choose a single band to illustrate the calculations of the Berry phase and the topological invariant number. If we discretize the loop, the one-dimensional loop with very dense k points, the phase difference between two nearest k points can be obtained by calculating the inner product of states of them. This term is also called the Berry connection. After we multiply all the Berry connections on the loop, we can get the Berry phase phi. The Berry phase is also called the linear charge center of this band. The Chern number can be defined on any two-dimensional manifold in the momentum space. It can be either a sphere or a cylinder. Here I choose the two-dimensional Brillouin zone. For each ky, we can define the one-dimensional Western loop around kx direction. Then we can calculate the linear charge center of this Western loop by studying the evolution of the linear charge center as a function of ky. We can get the topological invariant Chern number of these systems. The Chern number is equal to the Weyl number. For this case, the Chern number is 0, so this is a topological trivial case. For this case, the Chern number is equal to 1, so this is a topological non-trivial phase. Nowadays, many different topological states have been discovered. For topological insulating states, we can classify them based on their symmetry. Such as, for example, based on time-Rosser symmetry, we can define three-dimensional topological insulator and two-dimensional topological insulator. Based on crystalline symmetries, we can define various topological crystalline insulators. For the topological semimetal, we can classify them according to the shape and degeneracy of the band touching points. For example, if the systems have discrete band touching points, we can define direct semimetal or Weyl semimetal, and so on. If the systems has the line contact band touching points, we can define the node line semimetal or the node chain semimetal, and so on. Next, I will introduce our recent work. Here we studied a specific honeycomb lattice and the topological states in the lattice. Yeah, here we studied a specific A-stacked honeycomb lattice. There are only two equivalent sublattices A and B. A with basis PZ orbital is located at 0, 0, 0. B with basis DZ square orbitals is located at 1/3, 2/3, 0. So only three different symmetries are used to construct the Tadebani model. There are threefold rotation symmetry around the Z-axis, mirror symmetry with respect to the XOY plane, and the time-Rosser symmetry. The interactions are considered up to the next nearest interlayer hopping and the interlayer hopping. So then we can write down the Tadebani model easily. They are the band structures of the Tadebani model. The red bands represent the PZ tile bands. The blue bands represent the DZ square tile bands. For the dashed line and dot line, the angel values of the mirror symmetry are equal to I and minus I respectively. In this model, there are two different large bar splitting, which can be distinguished by the mirror symmetry MZ. In the configuration 1, the PZ tile bands and the DZ square tile bands have the same rush bar splitting. In the configuration 2, the PZ tile bands and the DZ square tile bands have the opposite rush bar splitting. Okay, let's focus on the configuration 1 first. If there is a band inversion at the gamma point, The band crossings around the gamma point will open band gap due to the same MZ, and the distance is a three-dimensional strong topological insulator. More interesting, when there is a band inversion at the K point, we can realize the Western metal phase. In contrast to the situation at the gamma point, there is additional phase for the DJ tail bands. The JJ of the blue bands will not change, where the JJ of the blue bands will decrease one. For this band crossing point, the two bands have the same JJ, so this is an anti-crossing crossing point, and will open band gap. For this band crossing point, there's a JZ jump. The delta JZ is equal to 2, so this is a double Weyl point. However, for the crystal with only threefold rotation symmetry, the double Weyl point is unstable and will split into 4 Weyl nodes. In the configuration 2, if there is a band inversion at the gamma point, the distance is a node line semimetal with 2 node lines circled around the gamma point. The node lines are protected by the mirror symmetry. If there is a band inversion at the K point 2, the two band crossings in the HK direction have JZ jump. The delta JZ is equal to 1, so they will not be gapped out, and the distance is a Western metal. It is interesting that we can realize a composite semi-metal phase with both Weyl point and the node line. As we can see in this figure, there is a node line in the XY plane, which is protected by the mirror symmetry. In addition, we can find a Weyl point in the HK direction. This is the illustration of the node line and the Weyl point in the brane zone. Okay, guided by the study of the tight bending model, we found the predict non-trivial phases can be realized in the materials RNSI. In the 330 space groups, only the space group 174 have the same point group as the tight bending model. Although there are few materials with the space group in the material database, we are so lucky and found the topological materials RNSI. This is a crystal structure of RNSI. The Rn and sulfur atoms are located in the XY plane, and from honeycomb lattice, the iodide atoms integrate to RNS layers. We found that lutetium sulfur iodide and yttrium sulfur iodide have the same Rashba splitting and are three-dimensional strong topological insulators, where the gallium sulfur iodide has the opposite Rashba splitting and is the long-pursued ideal Western metal with the Fermi level as the Weyl point. This is the band structure of lutetium sulfur iodide. If spin up coupling is ignored, there is the band inversion at the gamma point results into a node line circled around the gamma point. Of the consideration of spin up coupling, the node line will be gapped, and the distance is a three-dimensional strong topological insulator. On the 001 surface, we can find a single Dirac cone at the gamma bar point. In contrast to the well-known topological insulator, bismuth selenide, the surface state has the red-handed helical property. If we introduce the S-wave pairing, we may be able to realize the topological superconductor and the modular fermion in this material. As shown in previous slides, the modular fermion is very important, can be used to realize the topological quantum computing. Given the partial occupations of the F orbital of gallium, we propose 5 different magnetic structures for the gallium sulfur iodide, including 4 collinear magnetic structures and 1 non-collinear magnetic structure. We found the non-collinear magnetic structure has the lowest total energy and is the ground state of this material. Based on the non-collinear magnetic structure, we calculate the band structure of gallium sulfur iodide with the method RDA plus U. For the band structure without spin-up coupling, there is a node line in the XY plane and a Weyl point in the HK direction. which are consistent with overall titanium results. The partial density of state calculations tell us that the bands around the Fermi level are dominated by the pz orbital of sulfur atoms and the dz square orbitals of gallium atoms. In order to understand the band inversion mechanism of those materials, we studied the band involution process at the gamma point. We start from the atomic limit of those orbitals. In the step 1, the molecule bonding and the crystal field effect are considered. There is a band inversion between the P2 and D2 states. In the step 2, the spin-off coupling is considered. As the invited bands and the basis of our titanium models have the same GdSI, so the titanium model can be used to capture the main physicals of those materials. Okay, after the consideration of spin-off coupling, the node line in the XY plane will be gapped out due to the break of the mirror symmetry. However, the Weyl point in the HK direction will survive. The spin-off coupling will break both the transverse symmetry and the mirror symmetry. In order to build a titanium model for a gallium sulfur iodide, we add a Simin turn to break the transverse symmetry. For the break of the mirror symmetry, we use a trick here. There are two different hoppings of the SOC term, the interlayer hopping and the intralayer hopping. If we consider the interlayer hopping, the dispersion will change in the KZ direction but remain the same in the KX-KY plane. If we consider the intralayer hopping, the dispersion will remain the same in the KZ direction but will change in the KX-KY plane. Our first principle calculations show that the dispersions in the HK minus H direction are symmetrical with respect to the K point. So we only consider the interlayer hopping in this titanium model. Based on the titanium model, we calculate the band dispersions of gallium sulfur iodide, which are shown as the red dotted lines. It is clear that the titanium results fit the first principle calculations very well. We also calculate the chiral charge of the Weyl points. For the Weyl points located above the K point, the one-year charge center shifts downwards, which means the charge of this Weyl point is -1. This is the summary of the Weyl point distribution in the half-Brillouin zone with Kz greater than 0. On the 001 top surface, we can find the Weyl points are projected to the K-bar point, leading to this kind of gapless dispersion. On the 010 surface, we can find a very clean Fermi arcs. So gallium sulfur iodide is the long-pursued ideal Western metal with the Weyl point with the Fermi level at the Weyl point. I also want to emphasize the impact of the ideal Western metal. For the Western metal, one of the hallmarks is the chiral anomaly, which can lead to negative magnetoresistance. If the magnetic fields and electronic fields are parallel, there is an intervalley pumping of electrons between the Weyl points with different chirality. The intervalley pumping leads to unbalance of the left-handed electrons and the right-handed electrons. If we increase the angle between the magnetic field and electronic field, the magnetoresistance will become positive. Yeah, when the Fermi level is close to the Weyl nodes, the negative magnetoresistance will become more significant. So for the ideal Western metal, we can it is desirable to observe the large negative magnetoresistance. Another interesting result in the magnetic Western metal is the Anomaly Effect. When the Fermi level is at the Weyl point, the system has the largest anomalous conductivity. The whole conductivity decreases with raising the chemical potential. For the ideal Western metal, the system has the large transverse anomalous conductivity and small longitudinal charge conductivity. So the anomalous angle is large in the ideal Western metal, which is particularly important for the next generations of Hall devices. Okay, are there any questions so far?
It's quite clear to me. Yeah, great.
Okay. Okay, if there are no questions, I will continue the talk. Okay, next I will introduce the very recent paper. So here we study the magnetic semimetals and quantize the anomaly effect in the European boron 6. It is well known that the weld point doesn't need any symmetry protection except the translation symmetry. So it is usually very hard to find the Western metal. However, there is a specific system, the central magnetic central symmetrical system. For this system, we can define the topological invariant chi, which can be calculated from the parity of the occupied bands as the time reversal invariant momentum. If chi is equal to 1, the system cannot be gapped, and there must be band crossing points around the Fermi level. Generally speaking, it can be either magnetic nodalized semimetal or magnetic Weyl semimetal. Here we have studied the soft ferromagnetic material European boron 6, which has a cubical space group. We are interested in this material because its ferromagnetic order can be easily tuned. So we can manipulate the magnetic space group of this material, which is vital to realize different topological phases and corresponding topological phase transitions. Our calculation shows the ferromagnetic European boron 6 is an insulator, which is consistent with the previous measurement. In the low temperature, two ferromagnetic states have been observed. The ferromagnetic orders of them are parallel to the 001 direction and 111 direction respectively. In our paper, we call them FM1 and FM2 respectively. In addition, we also consider the FM3 state with the magnetic order parallel to the 110 direction. Our total energy calculation shows that the total energies of FM2 and FM3 states are very close. So it is also possible to observe the FM3 states in the experimental measurement. Of the consideration of the ferromagnetic order, we calculate the band structure of this material. The red bands represent the spin-up states. The blue bands represent the spin-down states. It is clear that we can find the spin polarization at the Fermi level is 100%. So we can only find the spin-up states at the Fermi level. Although the transport measurement found an incomplete spin polarization in this material, the spin polarization is very sensitive to the position of the chemical potential. If we dop the unit cell with 1% external electron, the chemical potential is increased by 0.30 eV. And the polarization will change from 100% to 50%. Okay, another interesting result in this material is in this band structure is the existence of the band inversion at the day point for the spin-up states. Due to the protection of the mirror symmetries, we can find 5 intersecting node lines around the day point. 3 of them are shown here. It is worth noting that the systems have 3-fold rotation symmetry around the 111 direction once the spin-up coupling is ignored. So the x, y, and z points are equivalent due to the rotation symmetry. So we can also find the node lines around the x point and the y point too.
Hi, Simin. It's quite an interesting slide there. So a couple of points here. So you said that this is ferromagnetism without spin-orbit coupling, but this is a europium hexaboride or something, right?
Yeah.
And so isn't europium pretty heavy?
Yeah, it's pretty heavy. Yeah, sure.
So why is there no spin-orbit coupling?
You mean the spin-orbit couplings? Yeah, I will consider spin-orbit coupling later. Yeah.
Oh, I see. So that's just a calculation without spin-orbit coupling.
Yeah. In the step one, we only consider the band structure without the spin-orbit coupling.
I see.
Then next, we will consider the spin-orbit coupling. Yeah.
I see. So then if you go to the next slide, you also had a so here they become spin polarized, and they become a ferromagnet. So what is the mechanism for this ferromagnetism? Is it orbital in nature, or is it because there's no spin orbit coupling going on here? So I'd like to try to understand what's going on
here. Yeah, here we just turn on the magnetic field. So there's a semimetal. So for the spin up and spin states, so the semimetal is in the diagonal semimetal is different. You can see for the spin up f orbitals are occupied, and it is located as a minus 1.5 eV maybe, and the spin down f orbitals are unoccupied. They are far away from the level.
I see. So is this a ferromagnet? You said you turn on a magnetic field.
Yeah, it's ferromagnetic.
So you say you turn on a magnetic field, or is this with a magnetic field or no magnetic field?
It is already with the magnetic field, but we didn't consider the spin-orbit coupling. This is the difference.
Oh, yeah. Okay. I'm just a bit confused because you call it a ferromagnet, and I just wanted to understand what the origin of spontaneous symmetry breaking was.
Yeah, I mean, so for this material, for ferromagnetic systems, I mean in the calculation part. So if you don't consider the spin-orbit coupling, you still have the time reversal symmetry. That's the difference. But after you consider the spin-orbit coupling, the spin doesn't matter. It means the energy for different ferromagnetic state will be different, and then you can, based on your calculation, you can find the ground state of the material. But if you didn't consider the spin-orbit coupling, the different magnetic order doesn't matter. You can specify your magnetic order without specify the direction of the ferromagnetic order.
I see. Is there a way of calculating, say, transition temperature from your code from this? Is there?
No. Okay.
So this is just like a rigid shift of your bands, of your spin up and spin down bands. Is that the point? I see.
Because for the first principle calculations, we assume we have zero temperature.
I see. Are you including some kind of Hubbard U or something, or?
Yeah, we are including Hubbard U. Yeah, this is why we push the F band away from the Fermi level. If you don't consider the Hubbard U, the F orbital will be around the Fermi level.
I see.
But Hubbard U, the effect of the Hubbard U is just to push the F orbitals far away from the Fermi level, either occupied or unoccupied.
I see. Thanks a lot.
Okay, no problem. Yeah, here we also consider the influence of the Hubbard U and the internal parameter mu on the band inversion. The red color represents the negative band gap. The blue color represents the positive band gap. As we can see, the band inversion with a negative band gap happens in the all parameter space in the spin up state. We also find the Hubbard U doesn't change the band gap of the spin down state. So then we consider the spin-orbit coupling of these systems. The different ferromagnetic orders can lead to different topological phases. We calculate the topological invariant chi of these systems and find the chi is equal to 1. So there must be band crossings around the Fermi level for this material. For the FM1 state, the system is a nodalized metal with 3 node lines circled around the X point, Y point, and Z point respectively. And those node lines are protected by the mirror symmetry, mirror Z symmetry. And on the 001 surface, we can find the Zimhar surface states, which are hallmarks of the node lines metal. Yeah, for the FM2 states, the node lines around the Z points will evolve into 2 Weyl points with opposite chirality. The Weyl points are constrained on the plane on the 1-1 0 plane by the symmetry time Russell times twofold rotation symmetry around the 1-1 0 direction. Similar analysis can be applied to the X point and Y point because for the FM2 states, the system has threefold rotation symmetry around the 1-1 direction. So the X point, Y point, and Z points are equivalent. So the system is a Weyl point, is a Weyl semimetal with 3 pairs of Weyl points. On the 001 surface, we can find the Fermi-arc surface states due to the presence of the Weyl point. For the FM3 states, the systems have the mirror symmetry with respect to the 1-1 plane. On the plane, we can find a node line circled around the Z point. The node line is protected by the mirror symmetry. In addition, we can find 2 Weyl points with opposite chirality around the X point. The Weyl points are constrained on the 001 plane by the symmetry time Russell times twofold rotation symmetry around the 001 direction. Similar analysis can be applied to the Y point, to the point Y2. So the system is a composite semimetal phase with both a node line and a Weyl point and Weyl points. On the 001 surface, we can also find the Fermi-arc surface states. As shown in previous slides, the anomaly effect is an interesting phenomenon in the magnetic semimetal. The anomaly conductivity is proportional to the distance between the positive Weyl point and negative Weyl point. For the FM1 states, the calculated anomaly conductivity is 0. This is because there is no Weyl point in the FM1 state, so there is no Weyl point displacement. For the FM2 states and FM3 states, the calculated anomaly conductivities are relatively small. This is due to the 2 following reasons. The first, the band dispersion of the node line is very large. Second, the hybridization band gap of the node line is relatively small due to the small intrinsic spin-off coupling of this material. It is well known that magnetic Weyl metal can be viewed as a state of quantum anomaly insulators. If the magnetic Weyl metal is made into thin film, we can realize the quantum anomaly effect. In order to study the topological properties of the thin film, we construct an effective K.P model for the FM2 Europium boron 6. Here, I would like to skip the tedious derivations and only show the results. This is the band energy evolution at the Z point as function of the thickness of the thin film. As it is clear that the band inversion successfully happens between the Hall subbands and the electron subbands. Based on the theoretical model, we calculate the topological invariant number of the thin film. As the OR model is a K.P model, the Western loop is a circle. Is a circle with the center at the Z point. Then we can calculate the one charge center of this Western loop. By studying the evolution of the one charge center as function of the radius of the cycle, we can get the topological invariant number of this thin film. So when When the thickness of the thin film is equal to 30 angstrom, the one charge center shifts upwards, so the Chern number is 1. As the systems have 3 equivalent Z points, so due to the threefold rotation symmetry around the 1, 1 direction, so the total Chern number of the thin film is 3. When the thickness of the thin film is equal to 60 angstrom, the total Chern number is 6. So the subsequent jump of the Chern number in this thin film is 3. We can realize a large Chern number in the thin film of FM2 European boron 6, which is important for the device applications based on the quantum anomaly effect. Okay, we also found some experimental signals of the non-trivial phases in the European boron 6. The R-path measurement found a Bohr gap in the ferromagnetic European boron 6. The transform measurement found an insulator to metal transition, which are consistent with our calculations. More interesting, the large negative magnetoresistance is also found in this material. So it is promising to observe the non-trivial properties in this material. Okay, this is the summary of the talk. First, guided by the study of a specific honeycomb lattice, we found a Lutetian silver iodide is a 3-dimensional strong topological insulator with right-handed helical substates, where the Galenian silver iodide is the long-pursued ideal Western metal. Second, we found different topological semimetal phases can be realized in European boron 6. For the FM1 state, it is a nodalized semimetal. For the FM2 state, it is a Weyl semimetal. For the FM3 state, it is a composite semimetal with both nodalized and semimetal. At last, we found the large anomaly effect can be realized in European boron 6, and the large Chern number quantum anomaly effect can be realized in its quantum Weyl structures. I also want to give an outlook of this field. First, although the non-magnetic topological states have been well studied, there are few magnetic topological states. Second, there are also a few topological superconductors. How can we find more candidates? For example, could we find intrinsic superconductor with well points in the normal phase? Then we may be able to realize the 3-dimensional time reversal topological superconductor. At last, it is urgent and desirable to design new algorithm to perform high throughput screening for topological materials. Okay, that's all. Thank you for your attention.
Thanks, Simin. So now I think the audience, you can unmute yourself and ask questions, or if you prefer, you can post your questions in the chat box. I will read it out for you. Any question from the audience?
Actually, perhaps let me start first. That was a very interesting talk. I had a question about, how large the anomalous Hall effect, how large Chern numbers could you get in this quantum well? That's one. And what is that origin of having Chern number larger than 1 for these quantum anomalous Hall effects? So it seems like you've drawn just one single edge state here. But you're saying it's large. You're saying it's large Chern number because of the right-hand side. Your sigma 1, 2 is 3 and there's 6, right?
Yeah.
So this is on the bottom right-hand panel. So my question is what is the origin of having such large Chern numbers in the quantum well structure of this Europium hexaboride?
First, the Chern number, because the subsequent jump of the Chern number is 3 in this material. So which means you can realize 3 and the Chern number is 3 and n is the number of jump. So you can
yes, of course.
You can reach as large as you want by increase the thickness of the thin film. That's
So as I understand, for example, the quantum anomalous Hall effect in a Weyl semimetal, as you nicely pointed out, actually just depends on the distance between the Weyl nodes, right? You just basically take the distance between the Weyl nodes K0 times E squared over H. This is because each kind of slice in between the Weyl nodes basically gives you a quantization of Hall conductivity. So I'm supposing right now when you're making this thickness D of this heterostructure D, what you're doing is you are basically confining it in this direction. So these are Weyl nodes, you're confining in this direction. And so am I just to understand here, these jumps that you see that go from 0 to 3 to 6, basically just come down to the quantization of Kz. Is that it, or is it more than that?
It's a quantization in the Kz. But so if you have two Weyl points, the number it just depends on how many Weyl points in the one side. But this is for the bulk. It's 3D systems. For that case, usually the number cannot be too large. But if you apply a quantization in the one direction, here I use the Z direction or one direction in this material. For the same field, that the situation is become different. So you can reach a very large height number, whatever it can be, but it must be the must be three and the multiple of 3.
And the multiples of 3 is Y again? Can you tell me? Is it because there are 3 copies or?
Yeah, because there are three pairs
copies,
of Weyl points.
I see.
That's
right. That's right. Yeah, I thought I saw only 2 pairs, but
this one.
Yeah. So okay, there's another.
The FM2 State.
I see.
This is
okay.
a 111 view.
I can't.
This is a 111 view of the FM2 State. If you use the slice to cut your brain zone, then they should be past 3 Weyl points with the same chirality. Once the plane pass 3 Weyl points, then the number is 3.
Okay.
After pass the other 3 Weyl points with the opposite chirality, that the number will become 0.
I see.
This is why we have 3 and in the same view.
I see. That sounds all right. Yeah.
But
great.
The number, the large number is very important for the application because you have more channels. The chiral gaprist channel on the boundary. That is, which means you can the signals of your measurement will become more obvious.
Okay, very good. Thank you very much.
So Simin, about the transport properties you mentioned in today's presentation, you mentioned like the negative magnetoresistance and the large magnetoresistance. So I think
this one.
Yeah, this one and also the next. Yeah. So my concern is that of course the chiral anomaly can induce this effect. This is interesting. But at the same time, it seems that chiral anomaly is not the only reason can cause this negative magnetic resistance. In other words, how can we know this is really due to the Weyl or it can be due to the other effects?
That's a very interesting question. Actually we don't know. Yes, because what we can know that one feature of the chiral anomaly is only when the magnetic field and electronic field are parallel, then you will have the chiral anomaly. The negative magnetoresistance. Once the angle becomes positive, the angle is not 0, then this magnetoresistance will become positive. That can say, this is the negative magnetoresistance is due to the chiral anomaly. But if you measurement from the magnetoresistance and it's not positive, once the magnetic field and electronic field are not parallel, then that is not convinced measurement results. only the theta of between the magnetic field and electronic field can give you the negative magnetoresistance.
Okay, I see.
And yeah, and you can see it's for this material that and you can see get for this right curve, so the magnetic field and the electronic field are parallel, then you get the negative magnetoresistance. Once the theta is equal to phi, then the magnetoresistance become positive, and it become more positive when you increase the angle.
So this is from Na3Bi or from which material?
No, this from the COSNS.
Oh, okay, I see.
Yes.
Okay.
Yeah, that kind of negative magnetoresistance is related to the current anomaly. Actually, so the negative magnetoresistance can be found in many, maybe many materials, but the whether the negative magnetoresistance appear only the magnetic field is parallel to the electronic field.
Okay.
Looks like Weyl has a question.
Yes, I do have a question. So for this
Okay.
EU B6, is there an estimation for the quantum anomalous Hall temperature? The transition temperature from the gap? Can you, is there some estimation of this critical temperature?
Temperature, how to say, because if you, I mean the ferromagnetic order appears as 17 Kelvin. So once you have the ferromagnetic order, then you will have the kind of normal Hall effect. The temperature is the ferromagnetic transition temperature.
Okay, but normally it's much lower than this.
There is a low, yeah. That is low. Yeah, the temperature is pretty low. Actually, yeah, our collaborators found that they must decrease the temperature until 10 Kelvin. There are some magnetic domains in these materials. Only the temperature is pretty low, then the domain will become large. That will give you the non-trivial box properties.
You said your collaborator already measured the quantum anomalous Hall?
Yeah, they are means they are doing the APAS measurements.
APAS measurement, I see.
Yeah, but nobody nobody is doing the transport measurements.
Okay.
I think the transport measurement is important because for the APAS measurement, the bulk gap is pretty small, as you can see here. Just only 10 million eV, so it's hard. It is hard to confirm in the APAS measurement. But the transport measurement will give you different anomalous conductivities that will allow you to distinguish the different topological phases.
Thanks. And also for this LuSI material, you go to the first band gap. You show that. You show the band structures. Oh,
You mean this one?
Yes. So do we need to avoid such cases? Because you see in this 001, so this cross points is not the ground state, right? So it's not. So basically, where do you need to tune the Fermi level to see this? This cross for the conduction band and valence band is not the ground state of the valence band, right?
I mean, this is a ferromagnetic material. There are no magnetization in this material. So because all f orbitals are occupied. So
maybe I see it wrongly because
you mean the Gaussian of iodine? That is.
So this is a colorful plot. This 001. You see this.
You mean here?
Yes, here the cross is not the ground state of the valence band, right? It looks so. Then
you mean the Dirac surface is not at the Fermi level?
Yeah.
But yeah, that doesn't matter. That doesn't matter. Yeah, you don't need how to the Dirac surface don't need how be the Fermi level, because for this material, if the Fermi level cut the surface state, you will naturally have a circle like surface states. You don't need for Bismuth sunlight. If in the ideal situation, the Fermi level is at the surface diachrone state. If we want to tune the if we want to make use of this surface state to realize the topological superconductor, you need to tune the Fermi level away from the Dirac point. But for this material, you don't need tune the Fermi level.
Okay, thanks.
So any other question from the audience? Okay, I have one question about the material searching. So
okay.
Yes, so we know the DFT really powerful in predicting new materials.
Yep.
But at the same time, we realize that not all the prediction can be realized in the future.
Yep.
So regarding your plan about the searching for materials, so what's your strategy so that you can, for example, we improve the accuracy of the stability of your calculations so that it can be really realized in the future by the experiments? So what is your strategy?
Yeah, my strategy is first the material must be already produced. Otherwise, no, the experimentalists will not follow you. Then for the non-magnetic material, because we know that the first principle calculations are pretty powerful for the non-magnetic materials. That is that is pretty powerful. The only problem is whether your material are so attracting for the experimentalists. Then they will follow. They will try their best.
Okay, so yeah, so you mentioned that it's really powerful in the non-magnetic. So
yeah.
How about the magnetic materials?
Yeah, for the magnetic materials, yeah, that's the problem. Yeah, because the DFT is usually not good to capture the electronic properties. So our strategy is we do the research. We read the paper first, and we find the signals of those materials, whether it is whether there are some existing signals of the non-trivial phases of those materials, because we know that the chiral anomaly is one of the hallmarks of the topological states, and not just the Western metal. Maybe Dirac metal, we can also find the negative magnetoresistance or the diagonal or magnetization. This the magnetization will become. We also show you some signals. Yeah, you should start from the experimental measurements. That will give you a background.
I see. So maybe just to kind of follow up that question, maybe you can ask kind of a more open-ended one since we have some time to discuss.
Yeah.
I don't know what the answer to this question is, and maybe you can give your opinion. So Weyl systems have been run for some time now. And it seems like, we're coming up with, more and more predictions of more materials, which have this kind of Weyl-like behavior. And so the question is why do we care? So why do we care to find more materials? So for example, there are a couple of materials, for example, like manganese 3 tin is quite a famous, well, maybe back in the day it wasn't, but now at least it's a fairly famous example of this kind of purportedly true Weyl point a material. So it breaks time reversal symmetry, has large nernst effect, has large anomalous Hall effect. I don't know if they've looked at Chiron anomaly yet, but so the question is, what do we gain from finding another example of a Weyl semimetal?
Yes, the first, so the Weyl semimetal have potential applications in the device application. So and another thing is, so in the materials, the Fermi level, it cannot be usually not at the one point, which means you will have some trivial hole or electron pockets that will give you some trivial signals, and it's not clean. And the other thing is the Weyl point. That if you have too many Weyl points in your systems, so which means the signals of the Weyl points is not easy to capture. And if we have magnetic fields, then we can explore the interpolation between the magnetic field and the Weyl point, as we show here. So it can have the Chiron anomaly. That because we already know that the magnetic, if the electrons, the magnetic fields will always increase the resistance, because the electrons are circular in the magnetic field. That will increase the resistance. But for the Weyl semimetal, the resistance will decrease. This is why you have the negative magnetoresistance. So you will have a very unusual transport measurement.
I see. Okay.
This is just the basic science.
No. I was just trying to understand.
Application, yeah.
No, sure. Okay. Great. Thanks.
Any other questions from the audience? So if no further questions, maybe let's call the end of this seminar.
Sure.
Okay.
Thank you, guys.
So let's stop recording.